Well, welcome to Lecture 3. In this 3, we will continue to talk about 2's complement. So the first idea that we'll consider today is to try to represent negative 10 as a 5-bit signed binary number in 2's complement representation. And so my advice to you is that whenever you have the goal of writing a negative number in 2's complement representation, that the first thing you do is to write the positive form of that number and then take the 2's complement of that to get the desired result. So our first goal here is to write positive 10 as a 5-bit signed binary number. Now, if it's going to be a 5-bit signed binary number, then that means we have one signed bit and then 4 other bits to contain the actual information about the magnitude of the number. Now, furthermore, since positive 10 is a positive number, the signed bit will be 0. So you can see here I've written sign, and we are showing that the signed bit is 0. And then we will have 4 other bits, and of course the rightmost bit will be the 0 position, and then the one to the left of that will be the 1 position, the one to the left of that will be the 2 position, and then the final one will be the 3 position. Now if we think about 10, and we think about this first position to the right of the signed bit, that's the digit that will represent the largest number, and in fact the number that it represents is 2 cubed, or 8. And so we ask ourselves, will 2 cubed, or 8, will that go into 10? And the answer is yes. So we have, in fact, we have 1 8 in 10. So we put down a 1 here, and that accounts for 8 out of 10s. So if we have written a 1 here, that means that the only thing that's left in 10 is, after accounting for the 8, the only thing that's left is 2. So now continuing to the right, this is 2 squared, which is 4, and there are no 4s in the 2 that we have remaining, so we put a 0 there and proceed to the next bit. Okay, this is 2 to the first power, which is 2, and there's exactly 1 2 in that 2 that we have remaining, so we put down a 1, and once we account for that 2, then there's nothing at all left, and so we don't have to go any further. We know automatically then that the last digit is 0, because otherwise, 2 to the 0 is 1, and there are no 1s in the 0 that we have remaining, so that's why we have 0 here. And so our final answer for writing positive 10 as a 5-bit signed binary number is 0 1 0 1 0. And we can check that. The 0 here is represented by this positive sign, and then this is 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the first power plus 0 times 2 to the 0th power, and we see that indeed that will turn out to be correct, because this will give us the plus sign, and then we have 8 plus 0 plus 2 plus 0, which is indeed positive 10. So that turns out to be just right. And now that we know that this is indeed the 5-bit signed binary number representing positive 10, then we can get the 5-bit signed binary number in 2's complement representation representing negative 10 by simply taking the 2's complement of this number. And there are different ways we've talked about getting the 2's complement. One would be to change all the 0s to 1s and all the 1s to 0s, and then adding 1 to the rightmost position. Or another way is to simply begin at the rightmost position and start moving to the left until you encounter the first 1. Leave that 1 as it is, but then after that 1, invert all of the other digits. And so let's think about that. Okay, this is a 0, so we continue moving. This is a 1, so we will keep that 1 as it is. So in other words, these first two, or the two most right numbers will be 0 and 1, but then we want to invert everything after that, so we'll have 1, 0, and 1. And sure enough, you see 1, 0, 1, 1, 0 here. That will be negative 10, written as a 5-bit signed binary number in 2's complement representation. So that's how we do that. Now, suppose that we wanted to write negative 10 as a 6-bit signed binary number in 2's complement representation. Well, once again, since this is a negative number that we want to write in 2's complement representation, my advice to you is to start by looking at the positive form of that number, getting it in the desired form, and then taking the 2's complement. So let's do that. Here we want to first write positive 10 as a 6-bit signed binary number. And so just as above, the first of the bits is the sign bit. And once we have accounted for that sign bit, since that's one of the 6 bits, then we have 5 bits left. And so we put 5 slots here, 1, 2, 3, 4, 5. And starting at the right, we number them 0, 1, 2, 3, and 4. And now we will proceed just as we did before. So if we move now from left to right, starting with the first digit, the first position to the right of the sign bit, we see we have a 4 here. So this represents 2 to the 4th, or 16. And there are no 16s in 10, so we write down a 0. Now we move to the next one. 2 cubed is 8, and there is indeed 1 8 in 10, so we write down a 1, and we think of having removed now 8 from this 10, so there's 2 left. And now we move to the right again. 2 to the second power is 4, and there are no 4s in that 2 that we have remaining, so we write down a 0 and move again to the right. This is 2 to the first power, or 2, and there is 1 2 in the 2 that we have remaining, so we write down a 1 here, and we think of subtracting 2 from that 2 that we had remaining, so now there's nothing left. And then move to the right one last time. This is 2 to the 0th power, which is 1, and there are no 1s in 0, so we write down 0 here, and we are done. So we have that this number 0 0 1 0 1 0 is the 6-bit signed binary number representing positive 10. And you can check that here. Here's the sign bit is 0, so that gives us this positive sign. And then we have 0 times 2 to the 4th, plus 1 times 2 cubed, plus 0 times 2 squared, plus 1 times 2 to the first power, plus 0 times 2 to the 0th power. And so this does work out to be positive 10. And so now that we know that positive 10 written as a 6-bit signed binary number is 0 0 1 0 1 0, now we take the 2's complement of that to find negative 10 as a 6-bit signed binary number in 2's complement form. And so again, to take the 2's complement, the easiest way to do that is start from the right and move to the left until you encounter the first 1. Keep those numbers the same, but then invert everything after that. So we have 1 1 0 1 1 0, and here it is, 1 1 0 1 1 0. So that's how we take care of that. That's how we write negative 10 as a 6-bit signed binary number in 2's complement representation. Now let's try, now let's review real quickly. Okay, the first thing we did was to write negative 10 as a 5-bit signed binary number. Then we wrote it as a 6-bit signed binary number. Now let's try to write it as a 4-bit signed binary number. So once again, we start by trying to write the positive form as a 4-bit signed binary number. And so just as in the two previous cases, we have 4 bits to work with, and the first one will have to be the sign bit, and then that leaves us 3 more bits. And so that will be numbering from right to left. That'll be the 0 bit, the 1 bit, and the 2 bit. And now we will proceed just as we have before. So we look first at this position just to the right of the sign bit, and that is 2 squared, which is 4. And notice there are 2 4s in 10. So we would need to have a 2 here. But remember, when you're writing binary numbers, the only 2 possibilities for each digit is either a 0 or a 1. We can't use a 2. And therefore, immediately this tells us that something is wrong. And in fact, we simply cannot write 10, positive 10, as a 4-bit signed binary number. The largest number that we can write as a 4-bit signed binary number is 0, 1, 1, 1, which is positive 7. But 10 is larger than that, so we simply can't do it. Now let's look at the idea of a subtraction problem. We have 2 signed binary numbers here, and we want to subtract the second number from the first one. So the top number is 11011, and the second number is 00111. And again, these are signed binary numbers. In other words, the first bit of each one is a signed bit. Now, one important thing to realize is that when you're doing this kind of a problem with signed binary numbers and you're subtracting one from the other, it is important to arrange so that both of them have the same number of bits. So that's if you are ever confronted with a problem where you're trying to subtract one signed binary number from another signed binary number, the first thing to do is to arrange it so that both numbers have the same number of bits. After you've done that, then you can proceed with the problem. In this case, both numbers already have the same number of bits, so we can proceed. And as we have discussed before, the easiest way to subtract one signed binary number from another one is to take this one that you want to subtract, and instead of subtracting that number, what you want to do is to add its 2's complement. And so that's what we have done here. We've brought the top number, we've just bring it directly over, 11011. But then this number here, instead of subtracting that number, notice that we've changed this to a plus sign, and now we write the 2's complement right here. And let's make sure that is the 2's complement. So remember, the idea for finding 2's complement, you move from right to left. After you encounter the first 1, you keep that, but then invert everything else. So we should have 11001, and indeed that's what we have here, 11001. So this number, 11001, is the 2's complement of this number, and we're going to add that to the top number to get our result. And let's see then what happens. So 1 plus 1 is 2, of course, so that's 0, and we carry 1 to the next location. And then this 1 and 0 is again 2, so we write 0 and carry 1. 1 and 0 is 1, and this time we carry nothing. 1 and 1 is 2, so we write down 0 and carry 1. And then here we have 1 and 1 is 3. So we write down 1, and this gets carried, and this carry actually just gets discarded. We don't worry about that carry at all. Now, we ask ourselves, this should be the final answer, but the only remaining idea that we need to check is the following. Are the two numbers here that we're adding together, do they have the same sign? If they don't have the same sign, then we're done. We don't have to worry at all. But if the two numbers here are either both positive numbers or both negative numbers, then we need to check one more thing before we're done. And in fact, in this case, both numbers are negative, so we need to check one more thing, and that is, did we get a negative answer? Because certainly, if we're adding two negative numbers, we must get a negative number. Just as if we're adding two positive numbers, we must get a positive number. So this is something to check. If you ever add two negative numbers and get a positive number, or if you add two positive numbers and get a negative number, either one of those cases means you have overflow. And in other words, you don't have enough digits to represent the number that you want to represent. That overflow will never occur if one of the digits if one of the numbers you're adding is positive and the other one is negative. In that case, if they have different signs, you never have to worry about overflow. But if both are positive or both are negative, you need to worry about this. So in this case, we have two negative numbers because of the side bit is 1 on both of them, but our result is a negative number as well, so we are confident that this is correct. Now, let's suppose that you want to check it to make sure, okay? So the way to check it, what is 11011? What is that number? We put a question mark here because we don't know what it is. Well, we know that it's a negative number, and so to figure out what it is, we'll look at the 2's complement. So 11011 complemented, move from right to left, and you keep this 1 and then invert everything else. So you have 00101, 00101, and now this is a positive number, and you can number the positions 0, 1, 2, 3 in the sign bit. So this is, because the sign bit is 0, this is positive, and there's no 8s, but there's a 4 and a 1, and 4 plus 1 is 5. So this number right here is positive 5, but remember this number right here is the 2's complement of this number, so this number must be negative 5. Similarly, for the second number here, remember we're adding these two numbers together, so this second number, what is it equal to? Well, now, one way you could do this is rather easy. If we look over here, remember this number was 2's complement of this number. And this number, since this is a positive number, is easy to figure out. That's just 1 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0. So that's 4 plus 2 plus 1, or 7. So this number is 7. And therefore, this number down here, which is the 2's complement of this number, this must be negative 7. And that's what we have here. So here we're adding negative 5 and negative 7. So this number, if we've done everything correctly, this number should be negative 12. So let's check and see if indeed it is negative 12. So again, this is a negative, we're down here. And we're wondering, is this number equal to negative 12? Well, as usual, since the sign bit is negative, what we will do in order to find out what number this represents is we will take the 2's complement of it and then see what that's equal to. So if we take the 2's complement of this, moving from right to left, inverting everything after the first one. Now, when we move to right to left, from right to left on this number, we don't encounter the first one until we get here. So only these last two numbers to the left will get inverted. So we'll have 0, 1, 1, 0, 0. And that's what we have here, 0, 1, 1, 0, 0. The 0 in the sign bit location means we have a positive number. And if we number the other locations, 0, 1, 2, and 3, then this is 1 times 2 cubed plus 1 times 2 squared, plus 0 times 2 to the first power, plus 0 times 2 to the 0th power. So it is positive sign times 8, plus 4, plus 0, plus 0, or positive 12. So this number is positive 12, but this number is the 2's complement of this number. So sure enough, this number does represent negative 12, and so we see that everything here did work out right. When we subtract this number from this number, we do indeed get 1, 0, 1, 0, 0. So this was all done correctly. Now for a similar problem, and I encourage you, I hope that after all of the examples we've looked at, that this is pretty clear, and so I would encourage you to stop the video for a moment and try to do this one on your own, and then we can look at it together. So here we have 1, 0, 1, 1, 0 minus 0, 1, 1, 0, 1. And once again now, these are signed binary numbers, and so rather than subtracting this number from the first one, we will take the approach of adding the 2's complement of the second number. So let's find the 2's complement of this. Moving from right to left and inverting everything after we encounter the first one, then this will be 1, 0, 0, 1, 1. 1, 0, 0, 1, 1. The first number we just bring over, it's 1, 0, 1, 1, 0, so we just bring that over, 1, 0, 1, 1, 0. And now we want to add these two numbers. So 0 plus 1 is 1. 1 plus 1 is 2, so we write down 0 and carry 1. 1 and 1 is 2, so write down 0 and carry 1. 1 and 0 is 1, and don't carry anything. 1 and 1 is 0, and carry 1, and this last carry can be ignored. And now, are we done? No, we're not done yet, because we were adding two numbers here of the same sign, and so whenever you're adding two numbers of the same sign, you have to check. So let's check. Well, we added two negative numbers here. We know they're negative because the sign bit is 1, and yet we got a positive number. It is impossible to add two negative numbers and get a positive number, so therefore this is an example of overflow. And if you want to get some idea of why you got overflow, that is explained right here. The top number here is negative 10. We can see that by taking the 2's complement of this number. Since it's a negative number, we take the 2's complement of it, and that will be 0, 1, 0, 1, 0, which is the number 10, and therefore the top number is negative 10. And now this second number is a positive number, so that we can figure what that is. This is 0, 1, 2, 3. So this is 1 times 2 cubed, which is 8, plus 1 times 2 to the 4th. 1 times 2 squared, which is 4. So 8 and 4 is 12, and 1 is 13. So this is minus 10 minus 13, which is negative 23. Our total answer here should be a binary number representing negative 23. But the difficulty with that is that we just don't have enough bits to represent negative 23 as a signed binary number in 2's complement form when we have just 1, 2, 3, 4, 5 bits. We need one more bit, in other words, in order to write negative 23. And you can see that right here. Negative 23 written the shortest way to write negative 23 as a signed binary number in 2's complement form is this right here, And notice that that requires 6 bits rather than the 5 bits that we have right here. So now, you know, if you were given this problem on a test or on an exam, you don't have to do all of that justification. All you have to do is what we did here at the very beginning. Once you see that you are adding 2 negative numbers and getting a positive number, or you're adding 2 positive numbers and get a negative number, if either one of those things happens, that is overflow and you're done. Because this is the problem you're supposed to do right here. And it just can't be, you can't write the result of this as a 5-bit signed binary number. So let's see some questions now. Somehow this question, I'm not sure how the number was left out here, but this is problem 3.1. You were supposed to do a subtraction problem. The subtraction problem you're supposed to do is 0, 1, 1, 0, 1 minus 0, 0, 1, 1, 0. Both of these are signed binary numbers, and the possible answers are A, 0, 1, 0, 1, 1, B, overflow, C, 0, 0, 1, 1, 1, or D, 1, 1, 1, 1, 1. And once again, now that's problem 3.1. And then for problem 3.2, another subtraction problem, you have 0, 1, 1, 0, 1, minus 1, 1, 0, 1, 0. And the choices for this one are A, 0, 1, 0, 1, 1, B, overflow, C, 0, 0, 1, 1, 1, or D, 1, 1, 1, 1, 1. And then, as usual, there will be at least one more problem given to you in class. So that concludes lecture 3, and good luck.